Hello, everybody. So what I'm going to do is talk you through this because it will be more interesting, I think, if I talk you through it. And it is related to what we did in class Friday, but it may not seem so much when we first start talking about it. So there is a video for us to watch, and you can answer questions, all right? So after that, after we do this, you can go on there and watch it. Right now, let's really focus instead on this reading. All right, so today's lesson is about measuring distance and displacement. All right, the word displacement is not one you know. I don't think you use it in normal conversation, but it means pushing something out of the way or moving something from one place to another. All right, in this case, what it means is moving something from a home position, like home base on a baseball field, and then moving away from it and ending like on third base. The distance from third base to home then would be the displacement from home. All right, we'll talk further about that in case that didn't make that much sense. So the essential question here is, what's the difference between scalar measurements, scalar, and vector measurements? The reason we did the lab on Friday to start this is because I wanted you to have experience with vectors before we talked about them. Because now that you've plotted vectors, you've measured them and you went in the correct angle as well. So you use the meter stick, or maybe 2 or 3 meter sticks, to measure the distance, but you were always sure that you were at a right angle going north, south, east, or west. So that is what defines a vector measurement, a distance, but also an angle. All right. So the motion of objects can be described by words. Even a person without a background in physics has a collection of words used to describe motion, right? Like going fast, stopped, slowing down, speeding up, turning, provide a sufficient vocabulary for describing the motion of objects. So let's talk about those again. Even a person without a background in physics has a collection of words they use to describe moving objects. Going fast, stopped, slowing down, speeding up, turning, making U-turns. All of these are motions, descriptions of motions that we know about and talk about. So in some ways, talking about in physics, especially in this motion unit, there are going to be many things that are so familiar to you. The difference is that the way physicists describe it scientifically, there will be words you have to learn and ways you have to think about it that you've never thought about it before. All right? So, in physics, we use these words and many more. We'll be expanding upon this vocabulary with words such as distance, which we know, right? Displacement is the new word. Speed, velocity. Speed and velocity are very similar words, and acceleration. We know when you accelerate, it's like you're at the curb and you accelerate to get going into normal traffic. As we will soon see, these words are associated with mathematical quantities that have strict definitions. So one of the things that we're going to be talking about is that physics has a mathematical view of life. And those mathematical quantities make it easier for some of you and will make it harder for others of you to get comfortable with. All right? But the reason that scientists use math is it simplifies things. All right? It makes things very specific. All right? And that's what we'll be doing too. The mathematical quantities, so here's the word, quantities. All right? That means anything that we measure. So we could measure mass, or we could measure time, All right, those would both be quantities that are used to describe the motion of objects, can be divided into two categories. The quantity is either a vector or a scalar. All right, so I'm going to underline that right here. Until you did the vector, you didn't know there was a word for that, did you? But when you read a map and you're looking at distances and then how far you have to go this direction, how far you have to go that direction, you're also doing vector thinking. These two categories can be distinguished from one another by distinctive definitions. So scalars are quantities. We also know this by another word, and that would be variables. All right? All right, so remember that we've talked about variables before. We've talked about the mass of something, for example. But in physics, we'll be describing lots of different variables like distance, time. All right, we're used to thinking distance, time, velocity, acceleration. All right, lots of words, but each one of these are quantities. In fact, when we tell you the mass of something, we'll give you a number, right? And a unit, such as grams or kilograms. If we talk about distance, we'll give you a distance, a number, and also we'll tell you that it's in meters or centimeters. Time, we know, always has seconds or minutes or hours. Those are the units. And velocity, miles per hour is what we normally use, like miles per hour south to Tucson, miles per hour north to Prescott. All right, those would be ways we would express velocity. Acceleration, they're all called quantities, but scalars are described by magnitude alone. So that means we have to get rid of this one and this one because both of those need direction. All right? Vectors are quantities that are fully described by both a magnitude. Magnitude means size. The way you've heard this word the most is, it'll say earthquake magnitude 7.6. Like the recent ones in Turkey, the magnitude of those earthquakes, one was 7.6, the other was 7.4. Very large earthquake magnitudes. So the word in general means size. And we put size in terms of numbers, right? We'll have a number and a unit. All right, like 5 kilograms. All right, a number and a unit. That's a magnitude. All right. Vectors are quantities that are fully described by both a magnitude, size, and units, and a direction. We use north, south, east, west, but of course you can use a more specific directions as from a compass, right? As from a compass. Two very common vectors are down and up. You can see they're opposites of each other. All right, so conclusion. Classify the following measurements as either scalar or vector quantities. So, I did the first one for you. It says 5 meters. M stands for meter, as we probably remember from our vector course. It only has a number and a unit, so therefore we call it scalar. It doesn't have any direction associated with it, does it? And this says then what's the unit the variable is measured at? Since students have trouble with identifying vectors, that's the reason that I put this in. All right, just a second. You can see the problem I'm having is one of a plug. All right, let me plug this little guy back in. So the B says 30 meters per second east. So the unit is meters per second. This is the common way to express it. Meter per second. All right. So they expressed it meter per second, maybe because it's unfamiliar to you. So it has a number and it has a unit, meters per second. But what's different about this is it's a velocity going meters per second in the direction east. So this has to be a vector quantity. It has to be vector. It has a number and a unit, but it also shows us a direction. So that means when you write a vector, you have to have a number and a unit, and then you have to tell the direction. So go ahead and do C, D, E, and F. Go. Do those now. I'll wait for you. There's only one on here that I think might be confusing. So the units for D, let's look at this one. All right, we're given 20 as our number, degrees Celsius. So I want to show you that degrees Celsius, we also put that way. And when you see it this way, I think it's clear that that's just a unit. All right? It's just a unit. Degrees Celsius, degrees Celsius. So this one has to be scalar because all it has is a number and a unit. All right. So did you find that E and F are both scalar? And that C must be a vector because it has a number and a unit, and it also specifies the direction of north. All right. The second part of this is about distance and displacement. So are they the same? I have to admit that when I use them, I probably need to clarify to you how I'm thinking. Are they the same or not? All right, the essential questions is what is distance, what is displacement, how are they different? So we know the answer is no. All right, and how do you determine the distance and the displacement for any given motion? All right, so once again, we're talking about measurements, and how we would figure out things. So remember, what I like about physics and chemistry both is that we're not memorizing things. We're trying to learn vocabulary words to use them and to figure things out using them with the proper words so we can understand it better. That's what science is like in general, especially physical science, which is why I like it so well. All right. Now, distance and displacement are two quantities that may seem to mean the same thing, yet have distinctively different definitions and meanings. All right? And then I'll show you where the confusion and overlap lies. And then we'll talk about how you could tell the difference. All right? So distance is a scalar quantity, which means it only must be a number and a unit, right? Number and a unit. So for us, that was like 3.0 meters, 4.0 meters, etc. But it's a number and a unit that refers to how much ground an object has covered during its motion. All right? So how much ground an object has covered during its motion, how far a bicycle went. All right? How far an object went. Now, displacement, however, is a vector quantity that refers to how far out of place an object is. So displacement, it was where it should be, and now it's out of place. So this is where a word like the origin or home base come from. Home base. Let me capitalize it. In baseball, home base is where everybody is moving from and returning to. In a racetrack, everybody is, especially let's talk about like the Indy 500. They go around and around and around and around. So they return to the original after they make one circle. All right, so returning to home, returning to the origin. You also are like that when you think of how far your friend's house are. Oh, they're 2 miles from my house. So we're talking how far away from where we live something is. All right, so displacement is not an odd term that we don't understand. It's just we don't know that word. We don't know that word displacement. Being displaced means you're out of place or that you've been pushed out of where you belonged. All right, it's the object's overall change in position. All right. Now, to test your understanding of this distinction, consider the motion depicted in the diagram below. A physics teacher walks 4 meters east. All right. Let's see. 4 meters east, 2 meters south. Oh, 2 meters north. I put the origin at the wrong place, didn't I? Yeah, the origin should be right up here. All right, because that's where she's starting. She started walking 4 meters east. We would know how to measure that. 2 meters south. All right. 4 meters west. And 2 meters north. All right. So this is the first vector. All right. Then we did another vector. We put the tail of the second vector where the tip was. This is called the tip of the vector or the head of the vector. Or the head. And this part is always called the tail. All right, so we start the tail of the second vector. Then we have to start on the tail of the third vector right here at the end, right here. And then we do the last vector where from here we go up to the beginning. Oh my goodness. She came right back to where she started from. So at this point, let me use green. All right, so at this point, she is perfectly back to where the origin was, isn't she? Perfectly back to where the origin was. So if we measure the distance, so the distance from the last vector to the origin is called the result. I'll show you what it looks like. Is called the result, but I'm going to put another word. It's called the resultant. So when we took the distance that you had come to outside, and then we measured how far it was from where we ended to the origin, that was called, I said, that's the result of what we did, and the name for that is the resultants. All right? The resultants. So the point is the resultant here equals 0 because she came right back to where she started from. All right, the resultant shows the displacement from where we started. All right. So you standing at the origin, and then at the end, you and your flag were standing at the last one, and that distance from the flag to the origin was the displacement. So we had a more complex one than the one this teacher is showing. All right. Now remember, you can stop the video anytime you need to. So even though the physics teacher has walked a total distance of 12 meters, her displacement from the origin is only 0. During the course of her motion, she's covered 12 meters of ground. The distance is 12 meters. Yet, when she has finished walking, she is not out of place because there's no displacement for her. The displacement is 0 meters. Now, here's what I want to say about this, though. Each one of these lines is a vector, right? Yes. Yes. So when we talk down here, I'm going to comment more on that. All right, so displacement being a vector quantity must give attention to direction. The 4 meters east cancels the 4 meters west. The 2 meters south cancel the 2 meters north, which is why it ended up as a 0. Vector quantities such as displacement are direction aware. All right. Scalar quantities such as distance are ignorant of direction. So when we were plotting our using the meter sticks and going north, south, east, or west, we were plotting vectors. All right. So we plotted 4 vectors, which is why I call this a vector course. We plotted 4 vectors distance and direction to determine the distance from home or the origin. All right? Which is the displacement. So, remember from our outside lab that we found ourselves close to the origin at the end of our 4-vector plots. The final distance was measured from the last vector back to the origin. That distance and direction was the displacement. So we did do that. The distance and direction away from the home base, which we call the origin. The result or resultant was the displacement. We didn't measure the angle because we don't know how to do that yet, but it was northeast in both vector plots, both the one we did and the one we'll be doing in the future. All right, just because I didn't plan it that way. But so we could say whatever the distance, we would say displacement equals 3.75 meters northeast. And that's with the arrow pointing towards the origin. All right. So from where you were standing with your flag, all right, towards the origin was a northeast direction. So let's talk about our outside vector course. We plotted 4 vectors in 4 different directions, north, south, east, and west. So the north and south vectors are opposite each other. Let's call north positive and south negative. When you have opposites, isn't it okay to do that? East and west are opposites of each other, so let's call east positive and west negative. So the displacement from the origin was going to be the sum of these vectors. So 5 meters west and 3 meters east, we would give the west one a -5 and the east one a +3. So the sum of those vectors, -3, is -5 and +3, ends up being 2 meters west. 3 meters north and 4 meters south meant if we gave the north a plus and the opposite, the south, a negative, we ended up with +3 minus 4. So the sum is -1, which is 1 meter south. -1 meter would be 1 meter south. So that's how science deals with directions that are opposites, by giving them plus signs and negative signs. So here is the picture of these plotted. So I took the sum and I plotted 2 meters west with 1 meter south, and that should be the same sum that we got. So what I'm going to want you to do is measure the length of that vector. So remember, this length is 1 meter, all right, on our graph paper. So that will help you take the centimeter reading that actually is to create a scale. So at the end you'll say the scale is 1 meter equals, and you'll measure with your ruler what that distance actually is. I tried to make it 2 centimeters on our assignment the other day, but this may be a little bit different, so you'll have to measure it with your ruler. Okay, so measure the distance from the end of the second arrow to the origin, and it's going to be some number of centimeters. All right, and then measure how long this was, these lines were, in centimeters, and then you'll be able to say 1 meter equals a certain number of centimeters. All right, I don't have a ruler with me or I'd show you that. All right, now We have a series of conclusion questions. I want you to work on these and do very good answers. Remember, I want very specific technical answers, technical sentences, the technical details from this. So remember, I'm not going to give you credit if you just give me general stuff. I want technical details that shows that you have learned from this assignment. All right, so there's some two explanations. All right, I want you to read these and answer them. You can whisper, of course, to your neighbor, to try your partner, and see if that will help you out. All right, thank you. I'll talk to you later. Be sure you have all these notes. Goodbye.